let's compare if the sequence converges, and if converges, then to what? And the series converges, and it converges, then to what? So sequence is a list. I mentioned before, we'll keep mentioning. Sequence is a data. Dots, 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 dots. And we want to see if the dots has a pattern. Do the dots stick somewhere, stuck somewhere or not? Do they stick to some number or not? That means you start with a limit. You literally want to find a limit. 3 to the n plus 9 to the n all over 13 to the n goes to infinity. You find the limit, and whatever that limit is, that's the answer. That's it. So answer for sequence will be literally the answer for the limit. That's it. Because we're connecting the dots and see the pattern for the dots. Since sequence is a list, it's a data set. What's the answer, do you know? 0. How do you know? I would break it into 2 limits. 3 to the n over 13 to the n goes to infinity. Property of limits allows us to do that. And continuous functions. In 9 to the n, 13 to the n goes to infinity. Each limit is 0 because denominator explodes to infinity faster than the numerator, or because 3 over 13 to the n definitely shrinks to 0, just like 9 over 13 to the n shrinks to 0. Fraction times fraction times fraction times fraction, of course it shrinks to 0. Do you understand that though? Pizza, 1/3 of pizza that can give you a pretty good slice, you can eat it. 1/3 times 1/3, now it's 1/9. That's smaller size of slice. 1/3 times 1/3 times 1/3, even smaller. So if you multiply fractions, that means the result is shrinking. You will have very small slice of pizza. So that's the answer. Sequence, let's write down. This sequence converges to 0. That's it. Simple as that. You just find the limit. So on a test, if you see sequence, I put it in black. Sequence, I put it in black, and series put it in black. So you can see the word. If you look for sequence, just find the limit and answer. Converges to 0. The sequence is convergent. Converges to 0. The series is not that simple. And that is why chapter 8.1 is so not important, to be honest. Many of you noticed how simple it was. Because, yeah, it's not very important. We're never going to go back to that chapter 8.1 except for the test. Everything after 8.1 is very important. But then it makes it challenging. But have lots of applications. And I will show you some applications next week after the exam. NASA and other stuff is pretty cool. Serious. Let's get serious. This joke is only funny like second time. Let's get serious. Now I have a serious sum. 3 to the n plus 9 to the n over 13 to the n. N is from 1 to infinity. What is the difference? What is the difference? Series is a sum. That's too fat. Sum. Sum means those dots, which now it's like very hard to see. So let me show you this way. The previous dots, they had a pattern. Here it is. It was going up, going down, and then it has a pattern. Seems like it's stuck around 0, okay? That was the level of those dots. We noticed when we connected the dots that in the long run at infinity, it stacks around 0. The limit is 0. That's exactly the idea of the limit. However, now I want to find the heights. Sums are heights. This height, and this height, and this height, and this height, and this one, and this one, and this one, and this one. What do the heights do? And that takes us to the improper integral chapter, to be honest. And that's how we're going to connect at some point. Series and integrals. We're going to do it next week already. So, if you go back to the improper integral chapter, which is going to the exam too, by the way, 6.6. Here's the idea. Improper integral told us that in the long run, we might be adding infinitely many things, and it's still going to give you, infinity, even though they're shrinking to 0. So y equals 1 over x, this is the graph, shrinks to 0, but too slow. So all those sums keep adding forever. And there's so many of them that the area is infinite. This is the idea. Area is infinite. Too fat, but okay. While y equals 1 over x squared had a finite area, even though we're still adding infinitely many areas. Check this out. Since it also shrinks to 0, but fast enough, at some point, you see those tiny sums? They don't matter anymore. So area converged to 1. And that's why this terminology is the same. Area converged to 1 or area blew up to infinity. That means even though series as well can shrink to 0, the sequence, the data can shrink to 0. Sums might be infinite. So we have to figure this out. The divergence test, which you covered last time, tells you that at least we know one thing. The tails should go to 0 in order to converge. See, the tails for this integral, and in our case it will be series, are not going to 0. And by tails, I mean the limit, so the position. They are keep expanding forever. Well, then the series is going to blow up. So that's exactly the terminology I like to use. And that's I will show you right now. Divergence test. I'll review it quickly and explain you in a funny way. Divergence test. Divergence test shows you only if series diverges, but not converges though. So divergence test says tails should go to 0. Tails must go to 0. That's my funny way to explain it. But the official terminology is you find the limit of those an, just like we did, and it must be 0 in order to converge. Must be 0 in order to converge. It still might diverge, but at least it must be 0. It's a requirement. If, and that's the most important part, if, let's make it fat again. If this limit is not 0, thank you for the delivery. If the limit is not 0, then diverges right away. And that's why it's called a divergence test. Let me tell you this way. If the limit gives you 0, I call them tails, because there's like the ends, okay? The ends of the data, like what is happening at the very tails. If the tails do not go to 0, we abort the mission, we don't talk about the series anymore, we just say it blows up, it diverges. But if the tails do go to 0, that is not it's not enough to say it converges. They might go to 0 slowly. So we use another test. So if not 0, then diverges. But if it is 0, then there's no info. Need to use another test. No info. Use another test. And we're going to teach you other tests next week after the exam. I was supposed to be teaching you more tests this week on Friday, but I don't like doing that. I don't like to give new topic before the exam. But usually that's what's in the schedule. So I changed the schedule when I became a coordinator. We don't have a new topic this week. We covered 8.2, that's the last topic for the exam too, so your brain knows where we stopped. I like it better this way. So, I will explain you it in this way, check it out. I like to use a hedgehog as the example. I was taught using a hedgehog. Probably because hedgehog is very important in Russian Ukrainian culture. If you ever read Tolstoy, War and Peace and other stuff, sometimes you see that, milady, here's a hedgehog as a present of symbol of my love. So very important piece of culture. Hedgehogs are in our yards, fairy tales. Hedgehogs are smart, so they are kind, they help everyone. This is like a whole thing about hedgehogs. So if you hold an animal in your hands and you close your eyes and I tell you you are holding a hedgehog, do you believe me? The one thing you will definitely gonna do is to touch the top of the hedgehog because you're expecting it to be pointy, right? So you're touching it and it's not pointy. It's like soft or fluffy, but it's not pointy. And you're like, no way, it's not a hedgehog. That is a divergence test. You're checking the tails. They're not 0. No way that converges. You definitely know the series blows up. However, it doesn't work the other way around. With your closed eyes, you touch the animal and it's pointy. Does it mean it's a hedgehog? Not enough information. That's exactly what I'm saying. Not enough info. What kind of other animal it can be? Porcupine, that's the popular answer. What else? While I'm drawing, you think. What else? Sea what?
Sea urchin.
Sea urchin, that's a creative one. What else? Anyone else? What is else? Other pointy animals. Okay, I heard that one too. So there are more other pointy animals. That means if it's not pointy, we eliminate the idea that it's a hedgehog. If the tails do not go to 0, we eliminate even talking about the series. It diverges. That's why it's called divergence test. But if tails do go to 0, we need another test to check out what the series is doing. Just like with hedgehog, if it's pointy, it can be something else. That's the idea. So some students do draw me this picture on the final exam, and I'm very tempted to give extra credit for it, but I don't. Let's check. All of this theory was just to check what we're doing with our series. I'm taking the limit again of the thing I just found, 3 to the n and 9 to the n, all over 13 to the n. And I'm checking the divergence test first. Divergence test. It is still 0, so not enough in 4. No, in 4, use another test. So you will tell me, like, why did we even bother then? That is like a 0 step in general. 0 step to check if you're wasting your time finding the series or not. For example, this one, number 5. Check it out, check it out. So you'll be wasting your time finding if it's a geometric series or not. But why would you do that? What's the limit of this amazing fraction? K times k plus 12 over k plus 3 squared. What is the limit? 1. Because it's k squared over k squared at infinity. It's not 0 diverges. D and E. Got it? So it saves you lots of time. I will put one example like this on the exam, and you're supposed to waste time on this. You're supposed to check the limit for the series. That is D and E. But for the sequence, it's not. Let's compare it again. For the sequence, limit is the answer for your problem. This is the answer. For the series, it's not so simple because series are sums. We got 0, not enough in 4. You don't get 0, diverges. Make sense? So it's not the same thing. And I will put sequence series in a test, 4 problems. Okay, step 2. Then you have to use another test. We're going to teach you more tests next week, but we did teach geometric series. So let's look at this carefully and see it this way. 13. How should we rewrite this? From 1 to infinity. How should we rewrite this problem? Who can help me with that? Rewrite it so it's easier to work on it. Yes? Yes? Okay. Well, yes, we just worked on it in office hours. That's why, like, I know you know. You wanted to mention?
So you can put 3n over 13n.
3n over 13n.
And then another summation.
Yes.
9n over 13n.
Perfect. And what did you want to say, Charles? Do you have a next step or not?
I was going to literally just say that, and I have no idea what to do after that.
You do. Okay, tell me. 3 to the n over 13 to the n. How should I rewrite that? How should I rewrite that?
0?
Later. 0 will show up later. 3 over 13, everything to the n. That is a geometric series. Does it make sense? So we're setting it up to be inside of 1 power. That will give us a very clear view that those are geometric series, both of them. Geometric series. GS is a notation for geometric series. Well, also geometric sequence, but whatever. And we taught you how geometric series looks like. Geometric series has, geometric series converges if the common ratio by absolute value is less than 1. And then if that's true, then I would even know it converges to what? It converges to capital S, which is A over 1 minus R, where A is the first term. first term. Be careful with this. It's not always the same as R, or it's not always 1 and stuff. It's the first term. So we know when it converges. There's a whole theorem that proves why this is the case. And you're supposed to know it from Monday class if you have good notes. I can see that she gave pretty good notes on that. Well, you have my notes as well. I also did post her notes in the modules. You can. Oh, I didn't. I should do it. So this is what she taught you on Monday. This is what geometric series looks like. As you can see, converges if R is less than 1, diverges otherwise. And if it converges, then 2A over minus R, where A is not 0, A is the first term, R is a common ratio, common factor. And common ratio is better. So that's like a side note, put it in little cloud. That's like a side note. Now let's discuss those two series. The first series is 3 over 13 to the n, and from 1 to infinity. What is my R? R, common ratio. 3 over 13, exactly, I heard you saying. Good job. By absolute value, very fast, it's less than 1. Converges 2. And you start building the formula. S equals A, 1 minus R. 1 minus 3 over 13, that's what we just found. A is the first term. When you plug n equals 1, you get A. A is the first term, but when I plug n equals 1, it is 3 over 13. It's not always the same as R, so be careful with that. Simplify, and you get the answer. This is the first series. The first series is 3 over 10. 3 over 10. The second series, very interesting, but if the second series blows up, everything blows up. Because if the second series gives you an infinite sum, then there's no way the first number 3 over 10 will fix it somehow. If it's infinite, it's infinite. Same with improper integrals, we had it before. So I don't need equal sign. I will do R. What is R for the second series? 9 over 13, exactly. By absolute value is less than 1. Converges to sum. The first term is 9 over 13. Again, 1 minus 9 over 13 equals to 9 quarters. 9 quarters. Add those together, you get the answer. The sum of 9 plus, what was the other one? 3. 3 plus 9. 3, what was the, 3 to the n plus 9 to the n. Is it wrong? 13 to the n, 1 to infinity. Add those together and you get 3/10 plus 9 quarters, which is 15/120. Converges to this number. Yes?
Is it the first term the coefficient of the 9 over 13 to the n?
So the first term, so A. Are you asking about A?
Yeah.
A is the first term. Let me write it down. First term. And the first term happens when n equals that first number. And that first number can be different from problem to problem. Can be 0, can be 1, can be 5. It actually depends on the data science. You can start from data point number 5. When I plug n equals 1, I will get 3 over 13 to the 1. That's how I know that's my A. Sometimes it's to the 0, then it's 1. Sometimes it's to the 5, then it's going to be 3 over 13 to the 5. But it's always the first term. Definition is here. Check it out. Definition is this. See this isolated looking nicely A? This A is standing by itself because it's a first term. Very first term. It's not because it's just outsider. It's multiplied by R to the 0. So whatever is the very first term, that gives you A. If that makes sense. Let me know. Did I answer your question?
Yeah.
Thank you. Very good. Thank you. That was a good question. That's the answer for your homework question. What do you think about that? Converges to. Sequence converges to 0. Series converges to 51 over 20. Yes?
So when you split the series, what if one of the terms converges and another diverges?
Then everything diverges. The question is, what if one converges, another one diverges? She showed it to you in class last time. Check it out. If one blows up, everything blows up. Same with the improper integrals, which we will start reviewing right now. This one, this is your homework problem, which is here. 3 plus 9 to the n over 9 to the n. She showed it to you on Monday. One series converges 3 over 9 to the n. But the other one was 1. Sum of 1 is 1 plus 1 plus 1 plus 1. That's infinity. Or you can check divergence test. It doesn't go to 0. It's 1. So since half of it blows up, everything blows up. Make sense? Or it doesn't matter half or not half. Part of it blows up, everything blows up. Does it make sense? Good question. Good job, people. Very nice. What do you think about that?